Good morning, students. In this class, we will start with a new chapter, namely chemical bonding. First of all, we have to start with the basic definition of chemical bond. It is nothing but the force of attraction that holds two atoms or more atoms or ions also. The force of attraction which holds two or more atoms or ions together in different chemical species. Means in different chemical species, two atoms may be held by one amount of force of attraction, even two ions may be held by some force of attraction. Whatever the chemical species, the attractive force that holds them together is said to be a chemical bond. Usually atoms are of high energy and are unstable. That's why they have no natural existence. Atoms have no natural existence because of that reason. In general, atoms are of high energy and have no natural existence and are unstable also. That's why those atoms do combine to give molecules whose energy is less. Molecules are of less energy than atoms actually. So because of this reason, for the sake of stability, atoms combine with one another to give molecules whose formation is associated thus with the release of energy. So for example, hydrogen atoms combine to give H2 molecule along with the liberation of 434.72 kilojoules. See, the purpose of writing this on the board is, if I start writing the definition even in the class itself, it takes nearly the same session will take more than 1 hour. So we cannot cover all the concepts in less amount of stipulated time. For that reason, some definition part I am writing it on the board. Okay. So atoms are more energetic and less stable, hence combine together to give molecules that are less in energy. When compared with the atoms, corresponding atoms which are combining, a molecule is of definitely less in energy. That's the point we have to notice. For example, hydrogen atom's energy. For example, some rough value you take. 1312 kilojoules for each hydrogen. 1312 kilojoules for each hydrogen. When these two hydrogen atoms combine with one another to give H2 molecule, it was noticed that this 434.72 kilojoules energy is getting released. Actually, summation of these two energies is 2624 kilojoules. What is the total energy of the two hydrogen atoms that are combining? 2624 kilojoules. See, I am maybe poor in mathematics. You please go through the calculation part. And when it comes to the energy possessed by H2 molecule formed during this, energy was observed as 2190 because the balance is released out. So as we are directly discussing that this amount of energy is released, we can simply, but otherwise we have to find the energy of hydrogen molecule, energy of each hydrogen atom, then energy change of the reaction, which is called as enthalpy change. Don't worry, we are going to study this enthalpy concept in thermodynamics. Okay, energy is expressed at constant pressure at a given temperature. It is called with the term enthalpy. Heat content or energy content possessed by a system at constant pressure condition at a given temperature is called as enthalpy. Okay, that's a standard line. So enthalpy change or energy change that's happening during a chemical reaction can be calculated as enthalpy change of products or enthalpy of products minus enthalpy of reactants. That is 2190 is the energy of products or enthalpy of products minus 2624 kilojoules, whose difference is minus 434.72 kilojoules. So if you want to write the same equation, in a modern notation, see the same equation if you want to write, it can be given as H plus H giving rise to H2. Enthalpy change is minus 434.72 kilojoules. In this way, wherever in a chemical reaction energy is released out, when you express the energy change in terms of enthalpy change, released energy is always expressed with a negative sign. Do remember this point. In exothermic reaction, energy released is shown with a negative sign because energy is released out, products are with less energy. When energy is released out, products are left with less energy. So energy change can be calculated as less energy of products minus more energy of total reactants. Obviously, enthalpy change comes with a negative sign. This notation is very, very important. First of all, we have to predict what type of reaction it is, exothermic, endothermic, etc. Okay. So for exothermic reaction, enthalpy change is always given with a negative sign. Once again, as atoms combine to give molecules which are relatively less in energy, bond formation between atoms during the molecule formation is always exothermic. Formation of bond is associated with a decrease in potential energy. Formation of bond is associated with a decrease in potential energy. Likewise, when two chlorine atoms combine to give Cl2 molecules, 239.1 kilojoules energy is getting released. In modern notation, the same equation can be given as Cl plus Cl giving rise to Cl2. Delta H equals to minus 239.1 kilojoules. Same equation in terms of expressing enthalpy change, in terms of enthalpy change, it is coming with a negative sign. So, whenever enthalpy change is with a negative sign, it stands for the reaction is exothermic. Okay. Now, formation of bond is thus always associated with decrease in potential energy. That is, chemical bond formation is always exothermic. Okay. Even though one or two exceptions are there, they will be discussed separately. Now, if you observe the same thing in terms of a graph, here in 11th and 12th classes, even up to JEE advanced level also, every concept must be studied in terms of a graph or plots. Suppose potential energy of the combining atoms is plotted against their distance between. Okay, potential energy of atoms is combined against distance between the two atoms. See, initially, suppose the two atoms are at infinite distance. Initially, the two atoms are at what distance? Infinite distance. So, they are at infinite distance. Okay. Atoms are too small. Infinite distance means in centimeters itself, when you express that itself is an infinite distance for them. Because infinite distance means where there are no attractive forces between them. That's what it means. So, consider atoms are at infinite distance. So, when atoms are coming closer and closer and closer, what happens? They repel with one another. Because suppose this is one atom and this is another atom. So, their nuclei contains similar charges, positive charges. Outside their electrons also of similar charges, negative charges. When atoms are coming closer and closer and closer, at one moment, till one moment only attractive forces exist. Till one moment only attractive forces exist. After coming to certain close distance, like charges repel with one another. Electronic charges repel, nuclear charges also repel. Okay. So, at one but still they attract, because of attractive force they come closer and closer and closer. Because of this, what happens? They repel with one another. Whenever repulsions exist, to minimize the repulsion and to come close together, release of energy takes place. Why they are repelling? Because their energy is high. When their energy is decreased, they can come still closer. Even between two people also, when their egos are high, they cannot be close. When egos are reduced, they can be good friends. The same way, two atoms while coming close to one another, release of energy takes place so that they come still closer and closer and closer. The same way, if you observe this plot, when they are at infinite distance, their potential energy is, their potential energy is 0. But when they are coming close, their potential energy is decreasing. Of course, their potential energy is decreasing and at one particular distance, attractive forces are exactly compensated by repulsive forces. At that distance, a bond formation takes place. So, bond formation between two atoms takes place at their least potential energies. See, bond formation between two atoms takes place at their least potential energies. And at that least potential energy situation, the distance between the two nuclei or two atoms, the distance between two atoms is said to be bond length. That is called as bond length. Okay, in this way we can illustrate that bond formation is associated with a decrease in potential energy of the constituent combining species. Right? Now, immediately, so atoms are combining to give molecules. We studied that point. So, what sort of atoms do combine? Immediately that point must be studied. It was noticed that in the total periodic table, noble gases are chemically inert. They do not participate in bonding on their own. because they are having completely filled outer shell. Especially except helium, neon, argon, krypton, xenon, radon and newly discovered inert gas also, they are all having stable octet set of configuration. Because of having stable ns2np6 configuration, because of having stable ns2np6 octet set of configuration, that means a symmetric arrangement of atoms. These inert gases are highly stable and do not participate in chemical reactions. So that's the point to be noted here. Noble gases are chemically inert due to completely filled outer electronic configuration called as octet set of configuration, except for helium, which has 1s2, called as duplet set of configuration. And rest of the atoms in the periodic table, rest of the atoms combined do participate in chemical bond formation to acquire such a stable electronic configuration of nearest inert gas. See, once again, in the total periodic table, noble gases are chemically inert because of having stable outer octet set of configuration. Remaining all elements of the periodic table do participate in chemical bond formation to attain their nearest inert gas configuration. That's what the point immediately observed with respect to noble gases. And thus atoms are combining to give molecules. How many atoms are present in a molecule? That depends. A group of atoms which can exist independently is called as a molecule. First of all, what's meant by a molecule means group of atoms. Group of atoms which can exist independently in a stable manner is said to be a molecule. How many atoms are present in a molecule? That depends on the combining capacity. How many atoms, number of atoms per molecule depends on the combining capacity of that particular atom or all atoms, which is called as valency. Combining capacity of an atom is said to be its valency. Already we discussed about this valency 2 times. Once in basic concepts of chemistry and recently in periodic table also. Valency can be expressed with respect to hydrogen or oxygen or chlorine, 3 ways. Valency with respect to hydrogen is called as minimum valency. Valency with respect to oxygen and chlorine is called as maximum valency. We discussed a few more points also, like for elements having 1 to 4 electrons in their outer shell, and here see, outer shell sometimes is also termed as valency shell. You know why? As outer shell electrons are responsible, as outer shell electrons are responsible for valency, those outer shell electrons are also called as valency electrons, or outer shell is also called as valency shell. Because of this reason, outer electrons are called as valency electrons and outer shell is also called as valency shell. Okay, this is possible only for S and P block elements. For D block elements, ultimate S and penultimate D combinedly called as valency shell. For F block elements, ultimate S, penultimate D and T penultimate F electrons combinedly called as valency shell electronic configuration. We have to recap all these points from periodic table. Okay, as outer shell electrons are responsible for valency, outer shell is called as valency shell and the corresponding outer shell electrons are also called as valency electrons. Okay, now here to explain this valency, varying valency, if number of valency electrons are between 1 to 4, then valency with respect to hydrogen is equal to number of outer electrons or valency electrons. If number of valency electrons are from 5 to 7, then valency with respect to hydrogen is 8 minus number of outer electrons. Even these points also we discussed. And this is with respect to minimum valency. When it comes to maximum valency, always valency is equal to number of outer electrons. Always maximum valency is always equals to number of outer electrons. So already we did this point, a small recap. Now to explain this bond formation and types of bond, what are the attractive forces, what are the types of valencies, the first successful theory was given by Kossel and Lewis. The first successful theory was given by Kossel and Lewis. It was named as Kossel-Lewis theory. Kossel-Lewis theory of electronic valency. Means they explained, even though they are from different places, they are not a group of scientists, they both are from different destinations, but fortunately they had proposed the same thing. They had given the same postulate, similar points about valency. But the difference is Kossel explained about electrovalency, and Lewis explained about covalency. Okay, or covalency. Why? No problem. That's not an issue. Kossel explained about electrovalency and Lewis explained about covalency. What's meant by electrovalency? Valency shown either by gaining or losing electrons is called as electrovalency. Covalency means valency shown by sharing of electrons. Valency shown by sharing of electrons is called as covalency. So, electrovalency was explained by Kossel and covalency was explained by Lewis. According to this electronic theory of valency, inert gases are noble gases are chemically inert. So, already we discussed this point. Noble gases or zero group elements are chemically inert because of having ns2np6 octet set of electronic configuration. Rest of the elements do participate in bonding. How? Either by losing electrons or by gaining electrons or by sharing of electrons. So, which atoms lose electrons and which atoms gain electrons? Let us discuss once again. Suppose if you consider a rough periodic table here. These are 4 series actually. These are 6 groups. Now, these elements have 1 electron in their outer shell. They have 2 electrons. They have 3, 4, 5, 6, 7 and they have 8 electrons. Like these are alkali metals, 1A group and 2A group. We should remember both IUPAC numbering as well as old numbering also. This is called as 3A. Don't neglect this. In the NCERT textbook, this AB system was given in a reverse way. Okay, wrong print. This is called as 4A, this is 5A, this is 6A, this is 7A and this is 0 group. Now, let us study these elements with respect to their valency. These 1A group elements have 1 electron in their valency. To get octet, they need how many more electrons? Tell me. Literally, they need 7 more electrons. In electron affinity, we have discussed. First electron affinity may be exothermic. First electron gain enthalpy may be exothermic. But second electron gain enthalpy onwards, it is endothermic. You remember that? It's not so easy to gain second electron onwards. So, when second electron itself is very tough to gain, how can they gain 7 electrons totally? Right? So, it's very tough to gain 7 electrons, but it is very easy to lose 1 electron. That's why these alkali metals, 1A group elements, they lose 1 electron so that the previous shell configuration will be octet set. For example, you take lithium inert gas configuration. Lithium is 1s2, 2s1. If this 2s1 is given out, lost, lithium is left with a helium configuration, which is its nearest inert gas. Similarly, sodium, if you take sodium 1s2, 2s2, 2p6, 3s1. This is the outer shell configuration. If this 1 electron is lost out, then sodium Na plus ion is possessing a 2s2, 2p6, whose configuration, neon configuration, it is getting stable inert gas configuration. Similarly, potassium also 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. See, potassium readily loses this 1 electron to get the 3s2, 3p6 configuration of argon. Right? So in this way, all alkali metals lose one electron to get the previous inert gas configuration. Suppose this is lithium. Hydrogen position is not certain. No, lithium, sodium, beryllium, magnesium. Lithium will lose electron to get helium configuration. Sodium will lose electron to get neon configuration. Potassium will lose electron to get argon configuration in that way. So likewise, alkaline earth metals, 2a group elements readily lose how many electrons? 2 electrons, so that their ion will be bearing nearest inert gas configuration. This is what given. The rest of the elements participate in bonding either by losing electrons. These are the elements which are losing electrons to participate in bonding. And third is the 3a group elements, if they are metallic in character, they lose certain number of electrons. When it comes to 4a group elements, they can do both. They can lose electrons, or they can gain electrons, or they can share electrons. Means they readily shows electrovalency as well as covalency. Usually this electrovalency is shown by metals and strong non-metals. Okay. Usually metals shows electrovalency only. Non-metals shows both electrovalency as well as covalency. Means electrovalency is shown by gaining electrons. Non-metal readily can gain electrons. At the same time, they can go for sharing of electrons also. Like that, when it comes to 17th group elements, fluorine, chlorine, bromine, iodine, astatine, etc., they have 7 electrons in their outer shell. They need how many more electrons to get octet? Just 1 more electron. That's why fluorine gains 1 electron to become F-. Fluorine electronic configuration is 2s2 2p5. By gaining just 1 electron, its configuration will be changed to 2s2 2p6. Likewise, chlorine gains 1 electron to become Cl-, bromine Br-, side. And if you consider the previous element, oxygen, sulfur, selenium, tellurium and polonium, oxygen has 6 electrons in its outer shell, valency shell. So it needs 2 more electrons to get octet. That's why oxygen gains 2 electrons totally and become O⁻². Okay, so the electrovalency of oxygen is 2. Electrovalence of fluorine is 1. Similarly, sulfur also can gain 2 electrons and become S⁻², like that. So in this way, these elements readily lose electrons to get the nearest inert gas configuration, and these elements readily gain electrons. Oxygen is gaining 2 electrons to get neon configuration. Sulfur is gaining 2 electrons to get argon configuration. Likewise, fluorine and chlorine are gaining 1 electron to get neon and argon configuration. Remaining elements either lose electrons or gain electrons, and these are the elements readily can share electrons to get the nearest inert gas configuration. Okay, in this way the bond formation between atoms I was explained either by using electrovalency or by using covalency. And possible questions from this in competitive exams are: an element M has 1 electron in its valency shell. Only valency shell is responsible for the bond formation, right? We are aware of that point. That's why, see, so we need to study the valence electrons. Element M has 1 valency electron. Element N has 3 valency electrons, suppose. Then what is the valency, minimum valency? You follow minimum valency rule. M minimum valency is 1, N minimum valency is 3. Then what is the possible formula of the compound between them? M3N1. So in this way, by crisscrossing their valency, we can predict their compound possible. Okay, we can predict the formula of the compound possible. Suppose an element has 3 outer electrons. M has 3 outer electrons. N has 2 outer electrons. So M valency is 3, N valency is 2. On crisscrossing, M2, M3. This is all with respect to minimum valency only. This is all with respect to minimum valency only. This bond formation between atoms was explained with respect to octet rule. Still, there are some exceptions to octet rule. Exceptions to octet rule means some species, some molecules do not follow this octet rule. Okay, for example, lithium chloride. See, in this lithium hydride, for example, you take lithium hydride. Lithium plus and H minus. What is configuration of lithium? 1s2, 2s1, and hydrogen is 1s1. Now Li plus has one electron lost. No, it is 1s2. Hydrogen is also 1s2. See, neither lithium nor hydrogen had got octet set of configuration. Means they are having less than 8 electrons. They have duplet set of configuration. So these are exceptions from octet rule. Suppose there are some expanded octet also. Expanded octet. Expanded octet means suppose PF5. Here phosphorus formed how many bonds? 5 bonds. Phosphorus formed 5 bonds. You know that each bond is associated with 2 electrons. Okay, if you are not aware also, just remember that point. We are going to learn all these cases. Each bond is associated with 2 electrons. Totally, phosphorus has got how many electrons after bond formation? 2 plus 2 plus 2 plus, like this 10 electrons it has got. According to octet rule, an atom should get 8 electrons after bond formation to get stability. But here phosphorus has got 10 electrons. It is expanded octet. SF6 sulfur had formed 6 bonds. Again, the notation is each bond, usually bond is associated with the 2 electrons only. Odd electron bonds, we are now itself we are going to discuss. See, each bond is associated with 2 electrons. So totally sulfur has got how many electrons? 12 bonds, no. 6 bonds, no. 12 electrons. So this is also violation of octet. There are certain molecules which do not get 8 electrons. Means electron deficient molecules, they are called as electron deficient molecules. Like BCl3. Boron has only 3 electrons in its outer shell, and each chlorine contribute one electron. So totally boron has got 2 plus 2 plus 2. Boron has got 6 electrons only. After bond formation, boron has got 6 electrons only. So it has a deficiency of 2 electrons even after bond formation. Such molecules in which octet rule is not obeyed and still there is a deficiency of electrons to attain the octet rule are called as electron deficient molecules. Like this, there were some exceptions are also observed immediately when they had given octet rule. Now, to explain all these things, nature of bonding and types of bonding were explained immediately, for which Lewis had given Lewis electron dot model. Lewis had given an electron dot picture to explain the nature of bond formation, according to which suppose hydrogen has 1 electron, 1 dot or star, whatever it is, you can specify in any way. Lithium has 1 electron in the outer shell, only outer shell, not all electrons. See, when outer electrons are called as valence electrons, suppose you take a bigger atom, suppose potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Suppose this is the configuration of potassium. This 4s1 is called as valence electron. 4s1 electron is called as valence electron. Here nucleus will be there, no? This nucleus and the remaining inner electrons are called as core. That's a notation we have to learn. Of course, we are going to study a bit more in JEE and NEET classes. Okay, and these are all, as it is frankly limited to PU session, right? We are discussing a bit low. This is called as core, and the outer electrons are called as valence electrons. Valence electrons are distributed around the core, means a kernel. It is also called as kernel. Nucleus and outer electrons are collectively called as kernels. Okay, so there are some other notations we have to learn. See, Lewis electron dot model. Lewis electron dot model explained the presence of electrons in the outer shell. For example, beryllium. Beryllium has a configuration 1s2, 2s2. What is valence shell configuration? 2s2. The 2s2 is given as availability of 2 electrons. Okay, boron configuration is 1s2, 2s2, 2p1. This is the valence shell configuration in which boron has 3 electrons. Out of 5, only 2 electrons are core electrons. Remaining 3 are valence electrons. See, follow the notation. So, those 3 electrons were given by Lewis dot picture in this way. Sir, we studied that 2s2 2p1 pair. No, that phenomena was not followed here by Lewis. Lewis had just given electron dot picture in which the number of outer electrons were given with the single individual dots. Carbon has 4 electrons, 1s2, 2s2, 2p2. In the valence shell 4 electrons. So those 4 electrons are given as 4 individual dots. Nitrogen has 1s2, 2s2, 2p3. Those 5 electrons were given in case of nitrogen has 1, 2, 3, 4 electrons. Then fifth one they start pairing. Okay, oxygen 1s2, 2s2, 2p4. These are the valence electrons. Oxygen 1, 2, 3, 4, 5 and then 6. Okay, then they started pairing. And fluorine 1s2, 2s2, 2p5. These are the valence electrons. Fluorine 1, 2, 3, 4. Total 7 electrons. No, fluorine has in the valence shell 4, 5, 6, 7. Thus, it has one unpaired electron. In this way, Lewis tried to give us data about the number of unpaired electrons which are responsible for bond formation. According to Lewis, these unpaired electrons are the one that are going for bond formation. When it comes to neon, its configuration is 1s2, 2s2, 2p6. Neon 1, 2, 3, 4, 5, 6, 7, 8. So in this way, neon has no unpaired electron. That's why it cannot form bonds. Understood? Thus, Lewis tried to explain the bond formation using his electron dot picture. Thus, different types of bonds were known in this mode of study, namely ionic bond, also called as electrovalent bond, covalent bond, coordinate covalent bond, metallic bond. So, which we will discuss in our next session.